Assalamu alaikum. Today we're gonna discuss about the membrane potentials and action potential. We have already discussed about the basic concept of membrane potential. What is membrane potential? What is potential? What is resting membrane potential? And how the action potential is elicited. What is action potential? So, generation of resting membrane potential or membrane potential. Nerve and muscles are called excitable tissues because they respond to chemical stimuli, mechanical stimuli, electrical stimuli. Muscles demonstrate by the contraction, nerves by the integration and transmission, chemicals by the secretion of neurotransmitters on the synaptic clefts, and also glands by their secretions. Electrical signals that are in neurons. Electrical signals depend on two basic features of the plasma membrane of excitable tissues. Number one, resting membrane potential. Number two, ionic channels. These signals basically depend on these two things in the cell membrane. If the resting membrane potential is already being developed, then it will excite. And the ionic channels that would change the polarity or gradient. This polarity change in polarity or electrical gradient of the cell will lead to the positivity inside the cell and negativity outside the cell to generate or to elicit a potential, some maybe some strong stimulus of like these may end up in an action potential. Number one, ion channels. Ionic channels are there are many types and they are due to the opening and closing of their doors or their gates. There are four kinds of channels. Number one, leakage channels, open and closed randomly. Number two, voltage gated channels, open to a change in the membrane potential. Number three, ligand gated channels, open and close in response to the chemical stimulus such as acetylcholine. And mechanical gated channels, open and close in response to the mechanical stimulation such as touch or tissue stretching, like your Pacinian corpuscles and all other things. Resting membrane potential. Now, what is the resting membrane potential? The difference in the voltage across the cell membrane when the neuron or the muscle cell is not producing an action potential. It must be a negative value. When the cell is on rest position, there will be a negative potential across the cell membrane. That would be minus 90, minus 50, minus 70. The typical or an average value is minus 70 millivolts. You should remember this value and it should be asked by you again and again in your practical exam, in your viva exam. It is very much important. A cell that exhibits the membrane potential is called to be polarized. That is self-explanatory, that the cell exhibit a membrane potential that is called polarized. Why resting membrane potential is active inside and the cell relative to the outside? It is very important and some examiners very fond of asking this. There are 2 points in it. Number one, the resting membrane potential is 10 to 100 times more permeable to potassium than to sodium. Note that both having positive charge. Potassiums tend to leak out of the cell down its concentration gradient, carrying positive charge with it and unable to carry chloride and the other anions having negative charge outside the cell because chloride have higher concentration outside. That's why. potassium will leak out. It is very tricky and very low. It's leak out from the cell, while chloride having negative charge and other proteins having negative charge, they cannot go outside. Potassium leak out because against the concentration gradient, because potassium is low outside and potassium high inside, so it leak through the cell membrane. The next point is non-diffusible anions, protein, sulfate, and phosphate. They cannot leave the cell. That's why there is a negativity inside the cell relative to the outside of the cell. Yes. Now you can understand this is the potassium that will leak outside and the sodium leak inside. But these proteins, molecules with the higher sizes in chloride could not leave outside. And this is the potassium sodium voltage gated pump. It is pumping three sodium outside and two potassium inside. It means that this pump is also maintaining or stabilizing or creating a relatively negative environment inside the cell than the outside the cell. Now, the forces act on the cell membrane that are diffusion, the movement across molecules from the region of higher concentration to the region of lower concentration, electrical gradient, positive ions move from the negative area and negative ions move to the positive area, active transport, the transport ions against their concentration gradient. Most important example is sodium potassium pump. We have already just saw the diagram of the sodium potassium pump that is pumping three sodium inside the cell uh, uh, and two potassium three potassium outside the cell and two potassium inside the cell, creating a relative negativity. These forces are responsible for maintenance of resting membrane potential so that the electrical integrity or electrical gradient of a cell should be maintained. It neither may shrink or it neither may swell. The development of action potential, very much important, and bringing the cell back into resting state after the action potential is over. Yes, when there is an action potential occurs, it will help in coming back the cell membrane in its normal resting membrane potential position. The action potential. What is an action potential? The action potential is a sudden reversal of membrane polarity by a stimulus. Importance. Action potential occurs in a living organism to produce physiological effects such as transmission of impulse along the nerve fibers, release of neurosecretions of chemical transmitters in the synapse, contraction of muscles, and activation and inhibition of glandular secretions. As in the start of the lecture, I have told you about the importance of action potential. That if the action potential in the nerve fibers, they will transmit in a chemical stimulations, the chemical transmitters in the synapse, such as acetylcholine. In the muscles, the action potential generate the response like contraction or movement, and in glands, it will activate and inhibit the secretion of glands. Development of action potential. When the cell membrane is stimulated by the physical or chemical stimulus, the cell membrane permeability to the sodium is dramatically increased. Obviously, the sodium channels open and the sodium ions rush into the inside the cell, causing the inside membrane to become positive with respect to the outside. This is called depolarization. I would explain in this diagram, the membrane potential becomes reversed and reaches to plus 35. This one. This is resting membrane potential, and here the sodium ions would rush in. They will be huge and sudden polarity difference, and the threshold that is of 0 that will cross above the threshold and reaches plus 30, and this process opening of a sodium ions causing reversal of the polarity at that area of the membrane and suddenly is called depolarization. Towards the end of depolarization, the sodium permeability decreases and the potassium permeability increases. Potassium ions leave the cell down their concentration gradient, causing the inside membrane to return quickly into its original position. This is called repolarization, and from here the potassium channels open slowly and it will move outside the cell, producing relative negativity inside the cell, and the cell membrane would try to gain its normal resting position, that is minus 70 millivolts, and this process, when sodium channels becomes to close and potassium channels begins to open and the plateau moves downward, it's called repolarization. Now we'll talk about the propagation of action potential. This is a normal resting membrane potential or resting condition of the cell. An action potential is elicited in the specific part, not in this end or not at this end. It may be start at this, at there, or this or there. The action potential elicited at any point on the excitable membrane usually excite adjacent portions of the membrane resulting in the propagation of action potential along the membrane. Action potential may be generated here like this, it will move along here, or it will move along like this. The transmission of depolarization process along a nerve or muscle fiber is called nerve or muscle impulse. As the action potential moves in their respective directions, this movement is called an impulse. Direction of propagation. It has no specific or a single direction of propagation, but action potential travels in all directions away from the stimulus. If this is a cell, this is a stimulus, it will move away from the stimulus in this direction, or in this direction, whichever the direction available may be, even along the branches of the nerve fibers until the entire membrane has become depolarized. Generation of action potential. Action potential actually divided into 5 phases. We will discuss each of them: resting potential, threshold, rising phase, falling phase, and recovery phase. Resting potential. When a neuron is at rest, only a small amount of potassium channels are open, permitting potassium ions to enter and exit the cell based on electrochemical forces. This is understandable. Threshold. As a depolarization stimulus arrives the membrane, a few sodium channels open, permitting sodium ions to enter the neuron. The increase in positive ions inside the cell depolarize the membrane, making it less negative. This is called threshold, making positivity inside the cell. Rising phase. Depolarization reaches the threshold potential. It means that there is a positivity going on inside the cell. Additional voltage rated sodium channels open. As the sodium ions rush because of concentration gradient from higher towards the lower concentration gradient inside the cell, the voltage across the membrane rapidly reverses and reaches the most positive value. This inside become positive and outside become negative. This the most positive value. It is called rising phase. Falling phase. At the peak of action potential, true process occurs simultaneously. First, many voltage gated sodium channels begins to close when the action potential has been achieved, like this. At this, sodium channels are beginning to close and potassium channels are beginning to open. Potassium channels are beginning to open, they are leaving from the cell. It means that the positive ions leaving from the cells and creating a negativity inside the cell to creating again that resting state, that is minus 70 millivolts or whatever the case may be, to maintain the normal position as previously. Many more potassium channel open, allowing the positive charges to leave the cell. This caused the membrane potential to begin to shift back towards the resting membrane potential, as already mentioned. As the membrane potential approaches the resting membrane potential or resting potential, voltage gated potassium channels are maximally activated and open to create more negativity inside the cell. Recovery phase. The undershoot occurs because more potassium channels open. This is the undershoot, rising, falling, and this one is the undershoot. The return to the steady state continues as the additional potassium channels that opened during the action potential are now closed. The action potential is now determined by the subset of potassium channels that are normally open during the membrane resting state. This is very good and illustrative diagram. This is minus 70 resting membrane potential at this one. Sodium channels open, the sodium begins to enter. At this, the potassium channels opens and begins to leave. At this, maximum number of sodium channels open here, and at reaching the peak, the sodium channels become refractory. This is the refractory. There is no movement of ions across the sodium voltage gated channels. At this, the potassium channels are begun open maximally. Potassium continues to leave the cell, causes membrane potential to return to the resting level. And the potassium channels closes, sodium channels reset. This one is resetting. And an extra potassium outside diffuses away. This extra potassium, which causes this line below the resting membrane potential, making it more negative, say is minus 80. The potassium ions that moved outside that will diffuse away. Resting membrane potential maintained by the sodium potassium pump. Depolarization, repolarization, depolarization. Sodium gate opens, repolarization, potassium gate opens. Refractory period, sodium gates cannot open, and resting membrane potential re-established by sodium potassium pump. All or nothing principle. It means that either the action potential is generated or not, yes or no. It's called all or none law. Applies most of the excitable tissues. The depolarization process travels over the entire membrane if conditions are right. But it does not travel if the conditions are not right. Either it causes action potential or it will not. A law stating the certain structures such as neuron, muscle fibers either respond completely or not at all. There is no partial nerve impulse in a neuron or a partial contraction of a muscle fiber. There is no partial contraction of a muscle fiber normally. In a disease, it can happen. If the stimulus is any strength above the threshold, the nerve or muscle fiber will either give a complete response or no response. If the stimulus can cause this movement of upward deflection of the graph, it will cause movement or no, yes or no. There will be no in between state. Refractory period. Refractory periods is a period when the cell cannot generate another action potential. It is the period in which an excitable cell cannot generate another action potential response to normal threshold. The word is normal. If the stimulus is much stronger than normal, it may cause another action potential. Otherwise, in one ongoing action potential, there will be no another or addition or another action potential in that. There are two types, there's absolute and refractory. Absolute refractory period which cannot initiate a second action potential even a very strong stimulus. There is no chance. The period coincided with the period of voltage gated sodium channels activation gates are inactivating and cannot reopen. They first must return to the resting state. It is the period where the voltage gated sodium channels gates are inactivated and they cannot be activated once they achieve the resting state. Relative refractory period. In this, there is a chance of second action potential, during which a second action potential can be evoked, but only if the stimulus strength is increased. Normally, the stimulus strength is like this. If the stimulus strength is much stronger, it may cause action potential at this interval or this period. The period when the voltage gated potassium channels are still open after inactivated sodium channels have returned to their resting state. It means that after passing or after completing the absolute refractory period, there is a period or interval where the second action potential can be generated. Yes, this is very good. This is the time from here to here. The second action potential cannot be generated, and this is the time where if stronger stimulus needed, action potential can be generated. Why the stronger stimulus? At this level it is minus 70, at this level this is minus 80, so it will be putting more efforts to create a stimulus from minus 80 to at this level as compared to minus 70 to this level. Less effort required as minus 70 and more effort, so more stronger stimulus is required at there to cause an action potential like this and attaining the resting membrane potential back. Plateau in some action potential. It is basically the normal action potential goes up, depolarization, repolarization, and normal hyperpolarization resting state. In this plateau, there is not sustained and continuous movement, but in this plateau, there is sustained and continuous movement. It especially occurs in cardiac cells when the heart has to pump the blood. If it is not contracted for some milliseconds, it may not squeeze out as amount of blood as needed by the body. The excited membrane does not repolarize immediately after the depolarization. Instead, the potential remains on the plateau near the peak of the spike potential for many milliseconds. This type of action potential occurs in heart muscles and fibers. The plateau ends when the calcium-sodium channels close and permeability to potassium channels increases. Here the sodium channel closes and calcium channels open. Here the calcium close and potassium open. In this type of action potential of cardiac tissues, the calcium channels would take part and play vital or primary role in a contraction of cardiac muscles for a few milliseconds to squeeze out a demanded amount of blood by the body. Rhythmicity of some excitable tissues, these are mainly concerned with the cardiac tissues, with intestinal tissues, or with some neuronal tissues. For example, in cardiac we have to be in a proper interval or rhythm required. In intestine we have to be a self-exciting tissue is required. We don't have to remind again and again about our heart to pump. Similarly, like in intestine, like in respiration, we don't even remember how many breath we took from since morning. Repetitive self-induced discharges occurs normally in the heart, most of the smooth muscles, and many of the neurons of the central nervous system. The rhythmical discharges causes rhythmical beat of the heart, rhythmical peristalsis of the intestine, and neuronal events as the rhythmical control of breathing. All other excitable tissues can discharge repetitively if the threshold for the stimulation of the tissue cell is reduced to low enough level. Even the large nerve fibers and the skeletal muscle fibers, which are normally highly stable, discharge repetitively when they are placed in a solution containing a drug, veratridine, which activates the sodium channels when the calcium channels or calcium ion concentration decreases below the critical level. So in these specific tissues, the threshold or the negative resting membrane potential that we already discussed is slightly lower. It may be -50, -60. So the repetitive action is repeated again and again to achieve that aim as required by the body. We don't have to give instructions, or we don't have to think about our heart pumping, our peristaltic movement that is done by the gut when we ate food. We don't have to instruct our gut that we are eating proteins or carbohydrates or fats, and their digestion should be according to that type of the food. Conductivity. Actually, conductivity is a message that is transmitted from one place to another. Or conductivity is an ability of nerve fibers to transmit the impulse from one area of stimulation to the another area. Action potential is transmitted through the nerve fiber as a nerve impulse. Normally, the body action potential is transmitted through the nerve fiber in only one direction, that is away from the stimulus. Away from stimulus. In myelinated nerve fibers, the connectivity is saltatory or jumping. In unmyelinated fibers, action potential will be continuous. Saltatory jumping means this is the myelinated nerve fiber. It is like this. It is very strong. Very fast. Much faster. It is 400 km/h, and in continuous, they will be slow and in one direction. This is for your reflexes, and this is for your pain. Your pain is very much continuous and irritating, but your reflexes, just like when you suddenly touch a hot subsurface or hot thing, you immediately withdraw. The myelinated, this is for your this example is for your understanding. So there will be a saltatory conduction like this, like this, like this, like this, like this, like this. This is very fast. Graded potentials. Graded potentials are basically the changes in the membrane potential that are confined to small area. For this area only, for this area only, or for this area only. small region or plasma membrane. Graded potentials of various names. It has got three types of graded potential: receptor potential, synaptic potential, and pacemaker potential. This is for only small area, like for this is this area, this is for this area, and this is for this area. Although the three of them combine to elicit action potential, but individually they cannot. There may be a small depolarization like this, but it cannot cross the zero or positive value like here. Or there may be hyperpolarization. It will become more negative. This is weak stimulus, this is strong stimulus, but even these two stimuli cannot reach the threshold or cannot reach the positive values and to create an action potential. Screenshot this differences table, the difference between graded and action potential. It is very much important. The amplitude is small. Amplitude varies with the size, obviously small. There is a depolarization or repolarization. There is no amplitude. Once the membrane is depolarized to threshold, amplitude doesn't matter. They have to go for action potential or not. Can be some 2 or 3 may be added. They cannot be. Has no threshold. They have specific threshold. Has no refractory period. They also have a refractory period. Amplitude obviously decreases with the distance. There is no effect of distance in this amplitude. Once action potential generated, it will go all along the nerve. Duration varies. Duration is constant. Walaikum Assalam. Dr. Waleed bin Talat has came to my room, that's why I have to stop. Initiated by the environmental stimulus, initiated by the graded potential. Obviously, the mechanism depends on ligand gated channels, mechanism depends on voltage gated channels. This is very important difference between graded potential and action potential. Thank you very much. I'll upload another lecture for resting membrane potential, for Nernst equation and all that inside concept that has already been pinching for the students. I'll try my best to get that.